Hello everyone. I'll be talking about this new work on list decoding of codes. We'll be constructing new explicit codes approaching generalized singleton bound using expanders. This is all based on joint work with Fernando Grana Jeronimo, Tushant Mittal, and Madhur Tulsiani. Let's start with the basics of codes. A code is simply a subset of sigma to the n, where sigma is some finite alphabet, and n is an integer called the block length of the code. The way these codes are used is we start with a message which can be seen as a k-length string over the same alphabet sigma. Here k is supposed to be at most n. So think of a smaller number than n. And this k-length string is then encoded into a code word, which is a member of the code. So in particular, it is an n-length string. And the whole point of doing this lengthening of the string is that when this code word is passed through noisy channel, the code is supposed to be designed in a way that it facilitates decoding even from a noisy copy of the code word. So this y that we sent over the noisy channel might get corrupted to y tilde. And hopefully the code is designed in a way that we can infer what y was even just looking at y tilde. And this is the part that is called as decoding. The code C is called linear if the alphabet can be identified with a finite field, and C is not just a subset, it's a linear subspace of fq to the n. The two most important parameters of a code are its rate and distance. The distance is defined to be, we look at all possible pairs of distinct code words in the code, and the distance is the minimum normalized Hamming distance between them. So throughout this talk, this delta y1, y2 notation will be using deltas for the normalized Hamming distance. Likewise, the rate of the code is this ratio k over n. So it is a measure of how much we are lengthening the string. When we started with x, the message was supposed to be a k-length string over sigma, and it was encoded, and the final string that we sent over the channel was n length. So the rate is a measure of how much extra cost we are paying, hoping to get this error correction property. Somewhat pictorially, let's say this is the entire space sigma to the n. The code words will look like a subset of this space. And the distance delta captures the property that any two code words are supposed to be somewhat well separated from each other. So if we look at any two code words, we have to change at least a delta fraction of positions to convert one to the other. Let's say we have this code word y, and when it is passed through a channel, it is getting corrupted to some y tilde. And the hope is that this corruption is not a lot. And in that case, in particular, if the corruption is less than delta over 2, then at least theoretically we can hope to map back y tilde to y, because if we draw a ball of radius delta over 2 around this y, then that ball uniquely belongs to y only. So if each code word draws a ball of radius delta over 2 around it, then these balls do not intersect at all. Okay. So given this intuitive picture, one thing that is clear is that we want the distance to be as large as possible because that enhances our error correction capability. On the other hand, the fewer number of code words that we have, the more redundant the code is, the more cost we pay for the error correction ability that we get. And as we increase the number of code words, maintaining distance for the same code becomes more and more difficult. And there is this tension between rate and distance. The most intuitive bound that captures this tension is called the singleton bound, which simply says that the rate of a code, the sum of the rate of a code and its distance cannot be more than 1. So for a given rate r code, the distance has to be at most 1 minus r. Okay. So ideally we want rate and distance to be as large as possible, but the singleton bound puts a constraint on the possible values of rate and distance. Remember, both rate and distance are numbers between 0 and 1. So ideally we would have wanted both of them to be as close to 1 as possible, but singleton bound will prohibit that. And really, at the end of the day, what we care about is the decoding radius, which is half of the distance. So this also says that for a rate R code, the best unique decoding radius we can hope for is 1 minus r over 2. Perhaps the most well-studied family of codes is the Reed-Solomon codes, which are based on bounded degree polynomials. So we choose f to be the messages of the code are in correspondence with degree Rn polynomials over fq, and then the code words are simply evaluations of this polynomial on n distinct points in the field. These Reed-Solomon codes are so popular because they achieve the singleton bound. So for a rate R code, um, the distance of Reed-Solomon code is 1 minus r. These are also encodable in near linear time and also decodable from the unique decoding radius, this half times 1 minus r threshold in near linear time. Reed-Solomon codes are used all over the place in many practical applications. They can also be used for constructing good binary codes via a standard method called concatenation of codes. And they also have a lot of theoretical applications. Reed-Solomon codes play an important role in fields such as pseudo-randomness, complexity theory, cryptography. So Reed-Solomon codes are very well studied. Um, they do have certain drawbacks though. Uh, First of all, as you can see, these are encodable and decodable in near linear times. There are codes that can do so with truly linear running time. And for Reed-Solomon codes, such algorithms are not known. The alphabet size, because we need n distinct points in the field to evaluate upon, the alphabet size must be of size at least n. Uh, and in general, this is one family of codes. It is not very flexible when it comes to incorporating other properties that we might want from the code. These drawbacks are answered by another family of codes called the Alan Edmonds Luby construction, or AEL. Uh, for the AEL code, the rate, if the rate is r, then the distance can be made 1 minus r minus epsilon for any epsilon that we want. So these codes can approach the singleton bound as closely as we want. So in fact, AEL should be seen as a procedure more than a single construction, where you can start from any base code that has rate close to 1, and this base code its distance can be amplified in a way such that the rate drops near optimally. So if the base code had high rate, it must have had small distance. That distance is boosted to 1 minus r minus epsilon, and then the rate drops from 1 to r. So the distance is boosted and rate drops near optimally. And in the process, the alphabet of the code becomes 2 to the poly 1 over epsilon. But recall that epsilon we can choose to be any constant that we want. So it can be small but a constant, and this gives codes that almost achieve the same behavior as Reed-Solomon, but with a constant size alphabet. The AEL construction was originally introduced to correct 1 minus r minus epsilon erasures in linear time. And it was later also used by Guruswamy and Indic to uh, encode and decode from 1 minus r minus epsilon over 2 errors in linear time. So recall that 1 minus r over 2 is the best threshold when it comes to decoding, at least unique decoding. And AEL codes allow us to do so in linear time. As I mentioned before, the alphabet size depends on epsilon, but not on the block length n. And it's a fairly flexible construction. So if the base code that we are amplifying the distance of, if it had some nice local properties like something called the LDPC property, where the membership in a code can be checked by very local queries, or LTC property, then such properties are also inherited by the final code when we do this amplification. Okay, so let's go into a bit more detail about what this AEL amplification looks like. The main tool that the construction uses is bipartite spectral expanders. Let's quickly recall what these are. So we'll deal with bipartite expanders that are biregular, so equal number of vertices on both sides. Let's say n of them, and the degree on both sides is d. We call it a lambda expander if we look at the L by R bi-adjacency matrix, and its second largest singular value is bounded by lambda times t. So if we take a complete bipartite graph under this definition, it's going to be a zero expander. And double cover of Ramanujan graphs can be shown to be lambda expanders with lambda something like 2 over square root d. So whatever lambda we want, we can find a constant, whatever constant lambda we want, we can find a constant degree infinite family of graphs with that strong expansion. Uh, and the key property from these lambda expanders that we are going to use is the expander mixing lemma, which says that if we are given any two sets S and T on left and right respectively, then the number of edges between those two sets is roughly the global density of edges times S times T. So S times T is the total number of edges that could have been between these two sets. And the graph is pseudo-random in the sense that the actual number of edges is going to be the global density of edges times the total number of slots of edges that we can have up to this lambda error. Okay, with this tool in hand, let's see what the AEL amplification looks like. First of all, let's say we have an outer code that is over large alphabet. If we have another inner code whose message length, whose number of messages is equal to the size of the alphabet of the outer code. So whatever is the alphabet size of the C out, if the number of messages for C in is equal to that alphabet size, then we can further encode each message symbol in C out to get a new code word for each coordinate of C out. And this is what is known as concatenation. AEL does a twist on top of concatenation where you do this concatenation so that the code word then lives on the edges of an expander. In the AEL amplification, all of this happens on the left side of the graph. On the right-hand side, we collect together all the symbols that we see on a particular right vertex. And then those symbols are then folded into a single big symbol. So since the degree of the graph was D, we will be receiving D many symbols on each right vertex, and we'll call all of them together as a single symbol. So the alphabet size will become the alphabet of the inner code, which is sigma in. The new alphabet is going to be sigma into the D. It can be shown that the rate of the AEL code or even the concatenated code is simply the product of the outer code and inner code. The distance is far more interesting. For concatenated code, it's again the product of the distances of the outer code and the inner code. For the AEL code, after this folding process is done, there is a decoupling between delta in and delta out. Previously, we were looking at a product of delta out and delta in. After this folding, the new distance becomes delta in minus lambda over delta out. So by making lambda small enough, we can make this delta as close to delta in as we want. Roughly speaking, the distance of the code gets boosted during AEL, because if we look at any two code words in this AEL code, then they are going to differ on a few left vertices. But thanks to this inner code, this means that a lot of the edges within these two neighborhoods are going to get corrupt. These two edges are going to be different for F and G. And because of the pseudo-random property of the graph, these different edges are going to go touch a lot of right vertices on the right. And wherever even a single differing edges touches, that right vertex is going to be counted as a difference between F tilde and G tilde. So on the left, these difference edges might be very concentrated on a few vertices, but thanks to the pseudo-random property, they cannot be very concentrated on the right then. Okay. So as we saw, the parameters, if the outer code had rate 1 minus epsilon, and we set lambda to be small enough, then we can get the rate and distance of the AEL code to be as close to the rate and distance of the inner code as we want. And notice that what is happening is we are getting an infinite family of codes based on the infinite family of expander graphs with the parameters of a fixed code which is of constant size because the vertex neighborhoods are of constant size, constant d. Those codes are of fixed size, but we are getting an infinite family of codes with similar parameters. Finally, we can choose this inner code to be a constant size Reed-Solomon code for the AEL code to approach the parameters of a Reed-Solomon code, which is essentially the singleton bound. But we don't necessarily need the Reed-Solomon code. We can also use random linear codes, for example, which also approach the singleton bound. Okay, so AEL codes provide a fairly satisfactory answer to the drawbacks of Reed-Solomon codes. But one field where algebraic codes have traditionally held an edge over any combinatorial construction is list decoding. So what is list decoding? We are concerned with the setting where the number of errors exceeds half the distance. So remember that for a rate R code, distance was bounded by 1 minus R, and because of that, the unique decoding radius was bounded by 1 minus r over 2. But we are interested in the setting where we want to deal with more errors than that. Uh, it still might not be a completely hopeless scenario if we allow the output to be a list of code words instead of just a single code word. So as we go for number of errors exceeding delta over 2, it will certainly happen that we cannot answer always with a unique code word. But the hope is that the number of code words will still be polynomial, if not 1. And this hope indeed comes out to be true because there is always a threshold called the Johnson bound, up to which the list size is bounded. And this threshold is always strictly between delta over 2 and delta. When the distance is 1 minus r, this threshold takes the form of 1 minus square root r. So note that by making r small enough, this threshold of Johnson bound can be made to approach 1, which is in complete contrast to unique decoding radius, which even in the best possible scenario can only be made close to 50% of the errors. Uh, the Johnson bound guarantees a combinatorial bound on the list size, but there is an associated associated algorithmic task of finding the list. Let's say this f tilde is the corrupted code word, then up to delta over 2, we know that there is going to be at most one code word. But beyond delta over 2, there might be more guys, but we are hoping that the list is still bounded. And the Johnson bound says that up to j of delta, the list is going to be bounded. Okay. So for Reed-Solomon, because the distance is 1 minus r, 1 minus square root r becomes a natural list decodability threshold. And Guruswamy and Sudan in their seminal works gave algorithms that could decode Reed-Solomon codes up to this Johnson bound. However, this is not the best radius that one could hope for. The best radius would be for a rate R code would be 1 minus r, and this is called the list decoding capacity. For example, this threshold is achieved by random codes and random linear codes, etc. No explicit codes that were list decodable up to 1 minus r were known for a while. And in the absence of these explicit codes, we also didn't expect a lot of algorithmic results that could decode up to 1 minus r. However, that changed with these algebraic constructions, in particular, this code called the folded Reed-Solomon code, which is a simple modification on top of the usual Reed-Solomon code that can decode up to 1 minus r minus epsilon errors for any epsilon greater than 0. This was building on the work of Parvaresh and Wadi, who also had similar codes that could beat the Johnson bound. By now, we have several variants of these codes that also achieve list decoding capacity, but all of these variants are algebraic in nature, and the proofs that these can be decoded up to the optimal threshold tend to be fairly algebraic. In terms of list sizes, the original Guruswamy Rudra proof showed that the list size is polynomial, but it was of the form n to the 1 over epsilon. This was improved by Guruswamy and followed up by Dweer and Lovett together, who showed that with some modifications using subspace evasive sets, the list size can be made 1 over epsilon to the 1 over epsilon. Later, Kopati, Ronzevi, Saraf, Wouters, they showed that folder read Solomon codes directly without any modification also have um, constant list size, the same sort of form of list size as proved by Guruswamy, Dweer, and Lovett using subspace evasive sets. Uh, Later, um, one of my work showed that the list size for folded read Solomon codes is 1 over epsilon square, and in an independent but concurrent work, Chen and Zhang showed the optimal list size of 1 over epsilon for folded read Solomon codes at radius 1 minus r minus epsilon. And all of this is focusing on the radius and the list size, but even in terms of running time, this list decoding can be carried out in polynomial time, and recently it was shown that it can also be carried out in near linear time. Okay, so in summary, we have optimal radius, optimal list size, and near linear time. So list decoding capacity achieving codes have been a great playground for the success of algebraic codes. Our main result is that AEL codes can, in many ways, match the performance of these codes. But again, as before, they tend to be more flexible. So we start from any uh, base code that has rate close to 1, and we can convert it into a rate r distance 1 minus r minus epsilon code. But it not only does it have optimal rate distance trade-off, it is also list decodable up to 1 minus r minus epsilon for any epsilon greater than 0. It is a combinatorial construction. In fact, the construction is same as the usual AEL construction. Um, the code derived using this, just like before, can be made LDPC, etc. And just constructing codes that were LDPC and achieve list decoding capacity was an open problem. The proof that these codes achieve list decoding capacity tends to be quite transparent due to its combinatorial nature. And it has usual AEL properties like linear time, unique decodability, etc. So all the nice properties that we saw before are still applicable in this construction. The list size is not just bounded, it's not just polynomial, it's actually optimal order 1 over epsilon directly. And as we saw for algebraic codes, this took a long line of work. Here, with the construction, you directly get an optimal list size. Uh, the alphabet size is also constant, unlike the folded read Solomon case where the alphabet size has to be growing with n. In fact, there the alphabet size is n to the 1 over epsilon. Here, the alphabet size is simply a constant dependent on epsilon only. In this work, we showed that these codes are also polynomial time decodable based on sum of squares hierarchy. In a follow-up work with Madhur Tulsiani, we also showed that these codes are not just polynomial time decodable, but actually near linear time decodable using regularity lemmas. One of the key insights in our work is that strengthening the property of list decodability to talk about not just the list size when we are talking about list decodability, but a certain stronger property allows us to give simpler proofs of this local to global transfer of such a property. So the specific property that we use is k-wise average radius list decodability. This average radius list decodability just says that we look at any G which is to be thought of as a corrupted code word or like a center of a Hamming ball, and any set H of distinct code words with the number of code words being at most k. It holds that the sum of distances of these code words from this fixed center G is bounded below by some number. So what this property is saying is that from any centroid, a set of code words is going to be far on average. How far? It depends on the number of code words. So if we are looking at k code words, then the sum we want it to be k minus 1 times 1 minus r. And if we are looking at, in general, cardinality of h many code words, then the sum of these distances should be at least h minus 1 times 1 minus r. So note that k equals 1, or h equals 1, we get the trivial case that the distance is non-zero. And for case k equals 2, we just get the triangle inequality, which is equivalent to the distance of the code. Importantly, the k-wise average radius list decodability means that up to radius k minus 1 over k times 1 minus r, the list size is going to be k minus 1. This simply follows by dividing both sides of the property above by k. That means that on average, the distance from the centroid is going to be k minus 1 over k times 1 minus r. So in particular, one of the code words must have distance more than k minus 1 over k times 1 minus r. And in particular, it must be outside of the Hamming ball. So the number of code words that can be inside the ball has to be at most k minus 1. And there exists something called the generalized singleton bound, which says that this list size of k minus 1 at this threshold is the best one can hope for. We cannot hope for a list size of k minus 2 at this threshold. And finally, by taking k to be roughly 1 over epsilon, we can approach the list decoding capacity, because then this factor of k minus 1 over k essentially becomes 1 minus epsilon. So this entire threshold of k minus 1 over k times 1 minus r becomes much closer to 1 minus r minus epsilon if k is large enough. Okay. Under this new property of average radius list decodability, what our main result says is that if the inner code is chosen to be k-wise average radius list decodable, then so is the global code CAEL that we get. And then the outer code can be arbitrary unique decodable code that is high rate. And all of this is, of course, under the assumption that lambda is small enough. For the choice of the inner code, it was shown by Al-Rabia, Guruswamy, and Lee that random linear codes are average radius list decodable. Chen and Zhang, their result about optimal list size for folded Reed-Solomon code actually also shows that folded Reed-Solomon codes are also average radius list decodable. So one could use either random linear codes from the AGL result or the folded Reed-Solomon codes from the average radius list decodable from the Chen-Zhang result. In either case, this is a constant size object, so we might even be okay with a brute force search. For example, even if we use a random linear code, we can afford to find such a code by brute force search. And because this local neighborhood is a constant, even if the number of even if the graph family is an infinite family, this search for the inner code is going to take constant time. So in summary, what our result shows is that list decoding is not just an algebraic phenomenon. In fact, more broadly, what we say is that expanders pack in sufficient pseudo-randomness for applications such as constructing list decoding capacity achieving codes. So before this, it wasn't clear whether existing pseudo-randomness primitives like expanders can achieve such properties, or is list decoding just a stronger pseudo-randomness property? One of the key advantages of our approach is that we directly achieve optimal list sizes, whereas for algebraic codes, we saw that there's the long line of work that slowly tries to get to the optimal list size. And a technical point that is a takeaway from our work is that strengthening the property from list decodability to this average radius list decodability, etc., that makes it easier to prove the local to global result. In terms of future directions, there is a close cousin of list decoding called list recovery. In fact, it's a generalization, and it also has a fairly well-established optimal list size that random codes achieve. And we don't know any explicit constructions that match that list size. There, it's also interesting because there are a lot of recent results that show that there are barriers to achieving that optimal list size for any linear code. So, is it possible that AEL construction is flexible enough to also achieve properties that are outside the scope for linear codes, but because AEL is such a flexible construction, it might be able to um, even achieve properties that are generally reserved for nonlinear codes. Um, there are also other applications of algebra and pseudo randomness. To what extent can we replace such applications by expanders or more basic tools? Um, one coding theoretic point that we made before was about the distinction between unique decoding times of Reed-Solomon codes, the algebraic family of codes which are near linear time decodable, and the combinatorial codes such as AEL, which are truly linear time decodable. Uh, does our code give hope? Our code gives hope for constructing codes with truly linear time decoding up to list decoding capacity. It would be very interesting to construct to come up with such algorithms, especially if they are more transparent and combinatorial in nature. And finally, all of this is for large alphabet. In general, it would be nice to have more uh, transparent picture of list decoding for binary alphabet, where we know very little and a lot of glaring open questions remain. Thank you.